I would like to introduce you to something that has taken several thousand engineers, several years to create. It is a masterpiece on many levels. It is the most complex project that has ever been undertaken. Arguably the most expensive computer project the world's ever done. Ladies and gentlemen, the Tesla Volta V100. This is made out of TSMC's 12 nanometer FinFET, and I'm just getting a little exercise up here. 12 nanometer FinFET. The part that is really shocking is this is reticle limits. Reticle limits basically means that it is at the limits of photolithography, meaning you can't make a chip any bigger than this because the transistors would fall on the ground. Every single transistor that is possible to make by today's physics was crammed into this processor. 21 billion processors, almost 100 billion vias, little connectors, 100 billion vias. To make one chip work per 12-inch wafer, I would characterize it as unlikely. And so the fact that this is manufacturable is great. It's just an incredible feat. 800 millimeters squared. If you guys have an Apple Watch on your wrist, the die size is approximately like that. Okay, so just take a look at your Apple Watch, gives you a feeling for it. 5,000 processor cores in here, 7.5 teraflops of 64-bit floating point, 15 teraflops of 32-bit floating point, and a brand new type of processor. A brand new type of processor called Tensor Core, which results in 120 teraflops of tensor operations. 120 teraflops. Unbelievable. This, the R&D budget is approximately $3 billion, and this is the first one. So if anyone would like to buy this, it's $3 billion. I'll just stick that in my pocket. The memory system in our architecture is quite unique. If you take a look at the way that most processors are organized, the register files are very small, the caches are very big, and the DRAM is quite large. In our case, the register file is huge, 20 megabytes of RF register file, so that the memory is very, very close to the processors, and that's one of the reasons why the throughput is so high. 16 megabytes of cache, and we're utilizing the state-of-the-art, the fastest memories that the world can make today. It's made by Samsung. Our partnership with them is terrific. The two engineering teams have been working so closely together, pushing the limits of how fast we can drive memories. And we've been able to achieve 900 gigabytes per second. It is just so fast. And then lastly, the second generation NVLink gives us 300 gigabytes per second, basically approximately 10 times the fastest PCI Express in the world today. Ladies and gentlemen, the Tesla V100. The Tesla V100 Volta has a new instruction inside. It's called the Tensor Core. It's a new CUDA tensor operation instruction that is both an instruction as well as data format. It's a 4x4 matrix processing array. And it basically does one of the most important primitives of deep learning, A times B plus C on a matrix. A times B plus C on a matrix. And so the input is A matrix, 4x4, 16-bit floating point, times B, 16-bit floating point, plus C. And we're trying to do that as fast as possible. So this is the way Pascal did it. And it did it incredibly fast at the time. And the reason why it's incredibly fast, every single row is multiplied by every single row is multiplied by every single column, and then when you're done, it accumulates, adds it all the way vertically into that green, the output results. And it does it incredibly fast because Pascal has thousands of processors. Because Pascal is doing this thousands of times at the same time. And that's the reason why Pascal was so fast. However, we felt that that just wasn't fast enough. What we should do is do it in parallel and in parallel. And so this is what the Volta Tensor Core does. It literally does the 4x4 multiply plus C at the same time. And it dumps it into result, 20 times increased throughput. Really crazy stuff. The net result is, although Pascal, the P100, is the most advanced processor the world's ever built, 1 year later, Volta is 1.5 times the floating point performance general purpose computing, 12 times the tensor operations compared to Pascal for deep learning training, and 6 times for inferencing. I'm going to come back to inferencing a little bit. Inferencing, for all of you who are not familiar, training the network is the first step. Very computationally intensive. And the second step, also computationally intensive, not as intensive, but computationally intensive, is inferencing, the production, the application of the network. Well, that's Volta, that's V100.